Hello and welcome to your background video for the Binary Chemical Reactions Lab. The purpose of today's lab is to practice working with chemicals and making observations. You will perform several reactions and record what happens. Using these observations, you will decide what type of reaction must have occurred to produce what you saw. You will also practice determining the reaction type just from seeing the chemical equation. As you watch this video and prepare for your lab meeting, try to use the example reactions given to form a general idea of what seems to always happen in each type of reaction so that you can predict the products of a reaction if you were just given the reactants. When you are performing today's experiments, you will be noting any properties or changes that you see. These changes may include pH or color change, formation of precipitate, liberation of a gas or bubbles, or a temperature change. Sometimes nothing seems to happen. For those, you can report your results as no visible change. Taking the pH of a solution is a great first step in being able to identify it, but be sure to take the pH of each solution before they are mixed. Since we aren't mixing our solutions quantitatively, observing the pH after the reaction occurs will do us no good. We would essentially just be getting the pH of the reagent present in excess. Because we're using pH paper today, our measurements will be rough and can only tell us if a solution is very acidic, slightly acidic, neutral, slightly basic, or very basic. Therefore, if your pH measurements are close together, you probably won't be able to differentiate between two unknowns. The visible appearance is an important observation. The color of a solution is an indication of what chemicals are present. We note the color of the solution before and after mixing, so make sure you record the initial color of the solution. A color change seems like an easy observation to make. However, be careful in identifying only actual color changes. For instance, if you had a blue solution and you mixed it with a clear colorless solution and it turned a lighter blue, this is probably a dilution effect versus an actual color change. We mentioned clear colorless solutions, so let's have ourselves a little chat. What color is this fine glass of soda? Students often answer clear. However, clear is not a color. Solutions like this can be described as colorless. This is also a clear solution, but clear refers to opacity and not color. So you try one. How would you report the color of this soda? If you said clear again, you're wrong. This soda is a yellow-green color. If I asked you what the opacity of the solution was, you could report that it was clear. So just to recap, opacity is whether or not you can see through it. So when you're answering questions about clarity, you can say that something is clear, cloudy, or opaque. Color describes the actual color. So the answers to these questions will be colors, like blue, green, purple, or colorless when the solution is lacking color. When a solution is cloudy or opaque, a precipitant is likely present. A precipitate is a solid that forms when two solutions are mixed together. You can see a precipitate because the ions that combine to form the product are not soluble. That is, able to stay dissolved in water and crash out of solution. Sometimes this will be very obvious, like with this reaction. Other times the solution may get sort of cloudy. If you wait for a while and some of the cloudy part settles to the bottom, you can say that a precipitate has formed. Schlieren, which are the blue streaks shown here, are often confused for precipitates because it appears that there is a difference between the two species. The important distinction is that Schlieren will go away when you stir your solution and a precipitate will not. If two reagents form a gaseous product, gas will be liberated from the reaction in the form of bubbles. A common example is a stereotypical vinegar and baking soda reaction from your middle school science lab. We don't expect big, exciting bubbles in our samples in this lab. Rather, you should mix the two solutions and wait a few minutes to see if small bubbles form on the bottom of the well plate. The energy of the reaction can be observed by a temperature change of the solution. We are not performing our experiments on a scale that allows us to measure a temperature change effectively. But if you're not sure whether a reaction is taking place, talk it over with your TA and decide if it's a good idea to do the reaction on a larger scale, say in a test tube. When you mix two solutions and you don't notice any changes, it's pretty easy to assume that no reaction has taken place. However, a number of reactions make products that are clear, colorless solutions which are soluble in our reaction mixture. Because of this, chemists use the term no visible change rather than no reaction. This implies that we didn't make any notable observations, but that we aren't willing to commit to the fact that nothing happened. There are two main types of reactions that we will be looking at today: single displacement and double displacement. Single displacement follows this general form. You can see that A displaces B to yield a new compound, AC. Single displacement reactions generally involve the transfer of electrons from one species to another. This transfer results in a change in oxidation state of two species. This is also called a redox reaction. Reduction and oxidation must always happen together. At this point in the semester, this definition may not make a lot of sense. The important pattern to note here is that the cation is displaced by another reactant, which becomes the new cation. The original cation typically returns to its elemental state. Double displacement follows this general form. You can see that each ion swaps partners to form the new compounds AD and BC. We will observe three types of double displacement reactions in this lab: acid-base, precipitation, and gas formation. Acid-base reactions are an example of an exchange reaction. They switch partners, and the typical products are salt and water. Acid-base reactions may not produce a visible change, but they are more likely to result in a pH change or a temperature change. You should deduce this type of reaction from the initial pH measurements. If you are not sure, then you might scale up the reaction to see if a temperature change occurs upon mixing. pH values after mixing are not a good indicator, as mentioned before. Precipitation reactions are a common exchange reaction. The cations and anions swap partners. One of the new pairs is insoluble in water, so it falls out of solution and suddenly appears in your beaker. The solution will often appear cloudy initially, and the solid will eventually settle to the bottom of the container. You predict the reactions that will yield a precipitate by using the solubility rules found in your textbook. Gas formation reactions are also exchange reactions. While it is not as clear as the other examples, it actually does follow the same pattern of cation-anion switching. However, the sulfurous acid that is produced will fall apart to form water and sulfur dioxide gas. This also happens when carbonic acid is formed, or when metal sulfides react with acids to form gaseous hydrogen sulfide. This should leave you prepared to design an experiment to examine these different reactions. Please go watch the short technique video as well as the balancing equations tutorial, and good luck on your quiz.